We've been dealing with limits as they approach single values now, and mostly we've been dealing with finite values for the outputs of those limits if they exist, right? And they may not. But we want to talk a little bit today about the idea of limits that might be just shooting off maybe towards infinity. But before we do that, let's take a look at kind of what the traditional definition of a limit is. So usually if I have some sort of function, and it doesn't have to be defined at the point that I care about, what I'm doing is I'm taking values near the x coordinate of the limit I care about. I'm kind of pinching those in. And as that window closes in the x values, what you see is that the window here in the y values closes. So what we have is some sort of bounding region, some sort of rectangle that should say as the x values get closer, the y values should also get closer. And that window should shrink down to this point so that the y value or the function value is equal to L. Now, in most textbooks you'll see this delta and this epsilon being written as like delta and epsilon, and that's the technical way to think about that, is it's kind of like a radius of a circle. But I think for pictorially it makes more sense to say basically as this delta gets smaller, the room for error, which is this epsilon, also gets smaller, and then the limit will eventually converge to what the function value would be at that point if it were defined, but it's not. And that's the idea of a traditional limit and how we've been doing it before. But when we talk about infinite limits, what we have are situations like these. So what we find is that some limits may increase forever. So as x gets close to a, the function value here just keeps going and going and going. It never stops rising. The problem is that it never actually reaches any point here. It just keeps rising. So it's kind of like riding the line without ever touching it. Think of it almost like I think of it kind of like drifting in a car. Like you're like, and you just keep on going. Drifting in a car doesn't quite work like that. But the idea is, in this case, whether or not we're coming from the left or the right, we're increasing towards positive infinity. So in this particular case, the limit here is actually infinity, and the definition of that basically, like the more formal definition, says that you can pick whatever number you want. I can always find a function value that's higher than that point. So you can say, oh well, 100 million. Nope, I can find a value of x really close to a that goes higher. Okay, 100 billion, even higher. 100 trillion, even higher. And that's the idea here, because it increases without bound. It means there's no cap on how high it goes. Now, we don't have to have the case where we go towards positive infinity. Sometimes we have the case where it goes towards positive and negative infinity. Notice in x equals b here, as I go up, as I come from the left, I'm going towards positive infinity. But as I come from the right, I'm actually going towards negative infinity. So we see as coming from the left, we go to positive infinity. From the right, we go to negative infinity. Now, in both of these cases, we would say the limit does not converge. But in this case, it depends on who you talk to. Some people will say that this limit still exists. It's just not finite. So we say the limit exists and is not finite, which means it doesn't converge because it doesn't actually hit some value. Like in this case, it would converge to a finite value L. But in this case, the limit doesn't even exist, right? Because remember, the definition of the limit says that the left and right hand have to agree, and in this case they don't. And we're going to do some examples using infinite limits and learn some techniques about how to spot when infinite limits are likely to happen.